This is content of part 7. If you're interested only in specific part of this video, just jump to its start time. Next, I will talk about the current dependency and gate wall dependency of anisotropy field and magnetic field, or induced by spin accumulation or offset field in short. The current dependency is important because the current modulation of both anisotropy field and offset field can be used for current-induced magnetization reversal and therefore as an effective recording mechanism in a 2 or 3 terminal magnetic random access memory. Mainly I will focus on how by current or gate voltage to reverse the magnetization of iron-boron nanomagnet. Since change of anisotropy field or offset field is not large, a key mechanism for the magnetization reversal is parametric reversal, and the key properties which is required for this mechanism is the current dependency of anisotropy field and offset field. So first I will explain current dependency of anisotropy field. This is a measurement setup which consists of non-magnetic tantalum nanowire with iron-boron nanomagnet on top of it. A Hall probe is used for measurement of magnetic properties of nanomagnet. All dimensions are in the range from a few to a few thousands of nanometers. A bias voltage is applied between two sides of tantalum nanowire and current flow through the nanomagnet. The electrical current which flows through the nanomagnet modulates the magnetic properties of the nanomagnet. The main reason why the current modulates the magnetic properties is a spin accumulation due to the electrical current. When current flows, spin polarized electrons are accumulated at the tantalum-iron interface, for example, due to the spin-Hall effect. Each electron has a magnetic moment, and the magnetic moment creates a magnetic field along the spin. Even so, the magnetic field created by one electron is small. In the group of spin-polarized electrons, all spin are aligned in one direction. The magnetic field is summed up and become large. When the magnetic field is directed in plane direction and perpendicularly to the equilibrium magnetization, the magnetic field tilts the magnetization towards in plane direction. This magnetic field is called offset magnetic field in short. When the direction of this spin accumulation created magnetic field is along the magnetization, it does not affect magnetization direction, but the value of anisotropy field. First, I will discuss the current dependency of anisotropy field. There are two types of the modulation of anisotropy field by current. The first component changes linearly with the current, and the second component is proportional to square of current. The change linear with current is about 100 Gauss per current density of 100 milliamps per square micrometer. The change which is proportional to current square is substantially larger. It's about 1000 Gauss per 100 milliamps per square micrometers. The recording current density in present MRAM is between 10 and 100 milliamps per square micrometer. So this current density is at upper limit for the magnetization reversal. Even so, the linear component is substantially smaller. You see, it is more efficient for the magnetization reversal because of its use in a very efficient parametric mechanism for the magnetization reversal. The linear modulation of the magnetization direction is one of key requirements for parametric magnetization reversal. This graph shows the anisotropic field measured as function of the perpendicular external magnetic field. The lines of different color correspond to different current density. Value of specific current density you can see here. Just by looking at the graphs, you may have an impression that the dependence of anisotropic field on the current is weak. It is a wrong impression because the anisotropic field changes substantially with external magnetic field, and that hides the current dependency a bit. The change with external magnetic field may be as large as 10 kilogauss. Only relatively to such a large change, the current-induced change may look small. These graphs show measured anisotropic field as function of current density. X-coordinate is current density at fixed external magnetic field. You can move here. You can see the change is not as small. In this case, the change of anisotropic field is as large as 100 Gauss. In addition, you can see clearly the existence of both linear and square components. The slope of linear components is negative. It is general tendency which exists for all nanomagnets I have measured so far. The anisotropic field decreases for positive current here. The negative slope is due to the geometrical asymmetry of this specific nanomagnet, bottom boundary of which is tantalum iron boron, and the top boundary is different from the bottom boundary, and it is iron boron MgO. A symmetrical nanomagnet does not have the linear component at all, this linear component. I will talk about it a minute later. This graph shows derivative of anisotropic field versus current density or the gate voltage. The x-coordinate is the outplane magnetic field in kilogauss. The modulation of anisotropic field does not depend on polarity of external magnetic field or magnetization of nanomagnet. Yeah, it's same for positive and negative part of external magnetic field. Additionally, there is no dependence on the scan polarity. The current dependency of anisotropic field is the same for two scans, along current and perpendicularly to current. The component which is proportional to square of current can be divided in two components. The first component is due to the thermal contribution, and the second component is due to the spin-orbit contribution. Since the used current density is relatively large, the nanomagnet is heated up a bit under the current. For the current density used, the heating temperature was estimated to be about 30–50 degrees. Even in some cases, the heated up temperature can reach 70 degrees. Due to the heating, the magnetization is reduced following the Curie-Weiss law. Since the anisotropic field is linearly proportional to the magnetization, the anisotropic field decreases with temperature. The heating power is proportional to current square. As a result, the nanomagnet temperature and therefore the reduction of anisotropic field is proportional to current square, like you see. Another contribution to change of anisotropic field, which is also proportional to I square, is a spin orbit contribution. This contribution does not depend on the sample temperature, but does depend on the sample structure, and specifically it depends substantially on the value of coefficient of spin-orbit interaction in nanomagnet. The current square spin-orbit contribution is substantial for multilayer nanomagnet having a large coefficient of spin-orbit interaction. Let us check the specific numbers. This data is the measurement for single-layer symmetric nanomagnet Volt 54A. Yeah, this one. This sample has a small and even negative coefficient of spin-orbit interaction. Yeah, this one. Minus. For this sample, both contributions, the linear and current square contribution, are nearly equal and small, of about 100 Gausses. For this nanomagnet, the current square contribution is mostly due to the heating. So next, let's check multilayer nanomagnet with high coefficient of spin-orbit interaction. Yes. This is data for wafer Volt 45B. It is a multilayer nanomagnet with positive and relatively large coefficient of spin-orbit interaction. Since this nanomagnet has many identical interfaces, it can be considered as a symmetrical one. As a result, it does not have any linear component, and its current square component is huge. The change of anisotropy field is about 1000 Gauss in comparison to only 100 Gauss for previous nanomagnet. Since both nanomagnets are measured at nearly the same current, yes, this is highest current, and therefore the heating and temperature was nearly the same, such a large change of anisotropy field cannot be caused only by the heating. Since this current square component clearly depends on coefficient of spin-orbit interaction, its origin in this is the spin-orbit interaction. I would like to mention it once again. Even so, it is so large. The current square component cannot be used as a parametric mechanism of magnetization reversal. As a result, this large component is not as useful. Next, I will talk about current dependency of offset field. It has only component linearly proportional to current. You may see. As we can see here, at least the linear component is dominated. The change of offset field is not large for single layer nanomagnet. It's only 15 Gauss at 100 milliamps per square micrometers. It is for this film, for this nanomagnet, single layer. But let's take a look for this nanomagnet. So change from this multilayer nanomagnet with high coefficient of spin-orbit interaction is significant. About 200 Gauss at 100 milliamp per square micrometers. It is important to note that this large current modulation of offset field in multilayer nanomagnet with high coefficient of spin-orbit interaction can be used for effective parametric magnetization reversal because the modulation is linearly proportional to current. You see, it is in contrast to the current modulation of anisotropy field, which is also very large in multilayer nanomagnet with a large coefficient of spin-orbit interaction. This large modulation cannot be used for parametric magnetization reversal because of its proportionality to the current square. For effective parametric reversal, it is important to adjust the magnetization direction of pin layer along the direction in which offset field changes due to the current modulation. In this case, the modulation of current will lead to the largest modulation of tunnel resistance. I will talk more in detail about parametric magnetization reversal in next video. You may recall that offset magnetic field exists even in the absence of any current. The electrical current just changes the direction of magnitude of offset field. These graphs plot two components of offset field along and perpendicular to current. A different color corresponds to a measurement at different current, and different dots correspond to measurement in different external magnetic field. From this graph, it looks like changing of offset field due to current and external magnetic field are perpendicular to each other. And from this, this is graph for single layer nanomagnet, like this. And from this graph we can conclude that direction of the pin layer should be adjusted to about 45 degrees with respect to current direction, like this. The case of a multi-layer nanomagnet like this is different. So just let's load it. In this case, the direction of pin layer should be adjusted along the current. The in-plane direction of equilibrium magnetization of the pin layer can be adjusted by the elliptical shape of nanomagnet. Next, I will talk about modulation of anisotropy field and offset field by gate voltage. In this case, gate voltage is applied between a nanomagnet and gate electrode, which is fabricated on top of nanomagnet. There is a gate dielectric between the gate electrode and the nanomagnet, so there is no current flow through the gate, and the magnetic properties of iron-boron nanomagnet is controlled by the voltage or gate voltage. It is important to emphasize that the gate voltage does not penetrate inside iron-boron nanomagnet because the iron-boron is a metal, and any voltage is screened by the conduction electrons. The voltage is only applied at interface between iron-boron and the gate dielectric MgO. Therefore, the magnetic properties of whole iron-boron nanomagnet is controlled by changing condition at the interface by gate voltage. I also would like to mention that the MgO is rather leaky dielectric, and in order to fabricate a gate dielectric using MgO, one needs a special recipe, which basically involves several steps of the Gauss interruption and several steps of annealing at optimum temperature. As a result, one can fabricate the MgO gate barrier of relatively high quality. Usually I use the MGO thickness of about 7 nanometers, which can withstand gate voltage of about 3 volts. Let's check the measurement data for the dependency of anisotropy field and offset field on the gate voltage, or the VCMA effect in short. This is measurement data for current dependency. The data directory ended with SOT. So let's go for the same nanomagnet, but VCM. This measurement data for gate voltage dependency, and we just store it in directory which name ended with VCMA. You see, let's copy paste this directory. So now line of different color corresponds the measurement at different gate voltage. Immediately one can notice one important fact, that the gate voltage substantially influences anisotropy field, but offset magnetic field is completely independent of gate voltage. The gate voltage does not influence offset magnetic field at all. This is a fact. So, if the change of the anisotropy field is about 100 Gauss per 1 volt of gate voltage, the change of offset field under the gate voltage is just 0. This graph shows the anisotropy field as function of gate voltage at fixed external magnetic field, which you can change here. This graph shows the derivative of anisotropy field with respect to the gate voltage as function of external magnetic field. This is data for the scans along and perpendicular to the current. The measurement data are absolutely identical, which is very much expected. Anisotropy field linearly decreases at increase of gate voltage. This feature is common for all nanomagnets I have measured so far. The slope here is negative. The derivative is negative. The dependency on the gate voltage may deviate from linear, like this, at higher gate voltages. The saturation may occur either at positive or negative gate voltage, here. I believe it depends on crystal quality and defect density in gate dielectric. Additionally, external magnetic field influences the strength of the VCMA effect. The VCMA effect decreases at larger external magnetic field, so slope becomes small. If you are interested to see the content and other parts of this video, you can find the links below this video.